Welcome to Homework Lib.
Hi there. So, for this problem, we have two radio antennas, one on position A and one on position B. And we want to determine the at what distance from B, that we call that distance S, at this point B, at what of that distance we will obtain destructive interference distances, because we can obtain various distance at which there are destructive interference. So the first thing that we need to calculate is the difference in path between the 2 points to the points P when where we are measuring the signals. So the path difference is given by the following formula, that delta x, that's the path difference, is equal to this distance, the distance from A to P, minus the distance from B to P. It is very straightforward to obtain that the distance from B to P, we're going to put in this, AP minus BP. So the distance of B to P is, as I said, very straightforward. The distance is S, but the distance of, of from A to B corresponds to the hypotenuse of this triangle, and that is the distance that we know, that is 200 plus x squared, which is this distance in here. So the path difference is that hypotenuse minus x, which is the distance between the points B and P. Now that we have found that, the next condition that we need to take into account is the condition for destructive interference. We are going to obtain destructive interference when the path difference, we're going to keep condition of destructive interference is delta x is equal to 2 times n minus 1/2 of the wavelength. We are not given the wavelength in the information, but we know the frequency. And we know that with the frequency and the speed of light, because light is the signal that is traveling, we can obtain the wavelength. So the velocity of light is equal to the frequency, I'm going to call this frequency times the wavelength. So solving for the wavelength, we obtain that the wavelength is just the speed of light over the frequency. So the frequency mega corresponds to 10 to the 6th hertz. So putting that values, we know that the speed of light is 3 times 10 to the 8 meters per second over 5.8 times 10 to the 6th hertz. So from here we obtained a wavelength of 50 meters. So that's the wavelength. So putting that value in this condition, so we'll obtain that we need to have this, and the wavelength is 50 meters over 2. Now, we know this expression, so we just put it in here. Is this in here? So that we obtain plus x squared minus x. This is equal to the condition for destructive interference. Now, we need to solve for x because that's the quantity that we want, the distance to the point B such that we obtain destructive interference. So we're going to solve for s. To do this, we see that we have a square root in here, so we elevate both of the sides of this equation to the square to eliminate that. So we can see that this is equal to this expression. We can see that we can simplify these terms because they are the same. And we just now need to solve for this x in here. So we will obtain and this from this we need to just um, put some values of n and then obtain the different values of the distance. So if we try n equal to 0, we will have the following. Gonna do that for this first one, and that is, sorry, the 0 is not in here. We need to take into account that the first minima occurs at n equal 1. So if we do that, let me just substitute that, it will be 2 here, it will be 2 minus 1, and that's 1, and this is just a meter square, and in the denominator we have 2 times 25 meters. So putting this into the calculator, we obtain a value of 787.5 meters. That's for n equal 1. So taking the value of n equal 2, we obtain x equal to 229.1 meters. You simply need to just put values for n. 1, 2, 3, starting from 1, because that's the first minimum. And for the third minimum, we know that is x equals 97.5 meters. And we can also obtain the fourth one, the fourth minimum, which is n equals to 4, which is 26.7. 26.7. I don't. I'm falling like a sleep. I'm and and that's it. We have obtained these four values of distances, and those are the distances from point B such that we obtain destructive interference at the point P.